Okay, my watch says 9. That says 8:59. We'll get started. So I had asked for you to do over the week-long break you had, right? What, 6 problems or so? Something like that? So if you could please turn those in. I think at the end of class last time I tried to hand out some of the unit circles, so I'll hand those out. What I'm going to do is just pass the stack around, okay? Everyone okay with that? Just going to pass these around. You go grab yours out of there. All right. So go ahead and please, if you could, get those problems, kind of clump them together and get them up towards this desk right here. Thank you. How was the graphing? Well, I can talk about it, yeah. Which one, 9 or 11? You pick. 9? Okay, before I get started on that, this is our plan. We're going to have our second exam on Monday, so a week from today. And it'll cover up through 8.3 as long as we get through 8.3. It just depends. Today we're going to cover 8.1 and then maybe start 8.3. It just depends on how far we go. And then Wednesday we'll do 8.3. We'll also have a review. And on Wednesday we'll have a review. So as far as like what you can bring to the test, you know, things like that, we'll talk about that on Wednesday. Let's focus on just moving forward. And then finally, I don't know who started this, but someone, either a faculty member or a student, thought that it would be a nice sentiment to put a little journal together. I don't know if you knew this, but your instructor, Christy, she had a 6 or 7-year-old son. She's a single mom basically, and so her son is kind of without a mom, and this little journal is for anyone who wants to write a little something to just kind of let her son know what kind of person she was. I don't know. I mean, it's here. What they've been doing is they've been letting students take it home and then bring it back and just pass it around. So if it takes, you know, a week or two to get this around, then that's how long it takes. But totally voluntary. Please come to me either after class and just ask, can I take that home? Or if you want to write something real quick, you can write something and give it back to me. But that, I just wanted to give you that opportunity. After it goes through this class, I have another class that I need to send it through. So that's here for you if you're interested. Okay, now the quiz, you got that also. Let me see, all right. So number 9. Yes, thank you. Number 9 was trying to graph y equals 4 sine pi x. Ooh, terrible. Pi x plus 2 minus 6. Everyone's turned in their stuff? So we know this looks like a sine function, right? Because it's sine. We know that the -6 here at the back, all this does is moves whatever this graph is, it moves it just down 6, right? So what we're going to do is we're going to focus on just doing a rough sketch of this, and then when we're done with that rough sketch, we'll move the whole thing down 6 units. Is it -5? Okay, well, I'll make it 5. Okay. So we'll start out with the actual sine function. Now the 4 tells us our amplitude, right? That just confirms that at the end we should have a taller than usual sine graph. There's no negative, so it doesn't flip it. But that all really doesn't matter if you follow the format of what we did in class, which was to take this right here and do what with it? Set it equal to 0 and 2 pi. So I'm going to start with that. I'm going to move kind of quick through this. Right? Up to 0. And then the other one, pi x plus 2 equals 2 pi. All right, so let me start with the first equation. If I first move the 2 to the right side, I get pi x equals -2, right? And if I divide both sides by pi, I get -2 over pi, which is a weird number, right? But it's still a number, right? -2 divided by pi is just some number. Now I'm going to go over here and do the same thing. I'm going to subtract 2 on both sides, so pi x equals 2 pi, take away 2. I can't do anything with that, right? 2 pi minus 2. I mean, I could figure it out as a decimal, but I'm just going to leave it like this. And then I'm going to divide everything by pi. Now, when I divide by pi, what you can do is you can divide each term on the right side by pi. So I'm doing this divided by pi, this divided by pi, this divided by pi. And the reason I did that on the right side, split it up, is because pi over pi will cancel here. So we get x equals, what? 2 minus 2 pi? 2 over pi? So maybe at this point you might have had a little trouble figuring out like where these numbers were, right? Yeah? Like, normally we're supposed to put those on a number line, right? And then break that up into different intervals to 4 equal sections. So which of these is smaller? Which one is on the left side? Which one is on the right side here? -2 over pi is on the left, and this one is on the right, because this is -2 over pi right here, right? This 2 means add 2, which means it's 2 units bigger, isn't it? So I can just go -2 over pi here. Then over here, 2 minus 2 over pi over here. So those are our 2 endpoints, right? And so what I'd like to do now is try and figure out where halfway is between those, right? What is halfway? So how did we do that halfway point? You could add them and divide by 2, right? So let me try that. If I take those 2 points, -2 over pi, I add to that 2 minus 2 over pi, then what happens when I put this -2 over pi minus this 2 over pi together? How many of them are there? What do you do when you have fractions that have the same denominators? When you're adding them? Add the tops, right? Let me put them side by side like this. Right, that's what I'm doing. I'm putting this one and this one together. So if I have the same denominator, all I have to, oh, I forgot to put the divide by 2. Oops, this whole thing's going to be divided by 2. This whole thing's going to be divided by 2. I added them, I forgot to divide by 2. So what would you get here? These two, -4 over pi, right? That's -2, take away 2, that's -4. So I have -4 over pi plus 2, and then all of this divided by 2. I know this is weird. That's probably why you're asking. It's, you know, these numbers don't always work out to be nice. If I want to divide this by 2, can I divide each of these by 2? Since there's 2 terms up here, can I do -4 over pi divided by 2 and then 2 over 2? Yes? Okay, so let me do that. I'm going to go -4 over pi. I'm going to divide that by 2, then plus the other one was 2 over 2, which equals. Now over here, when you divide this by 2, This is the same as dividing by 2 over 1. So I'm just rewriting it as a fraction over a fraction. And then remember, when we divide by a fraction, it's the same as flipping and multiplying times the reciprocal. So what would this become over here if I flip that up? 1, like that, it would be that, right? And this would be negative 4 over 2 pi, but the 4 over 2 would reduce. So you would have what? Negative 2 over pi, right? Negative 2 over pi. Are we okay with that? So negative 2 over pi. And then what was this right here? This is just 1, right? This is just 2 over 2 would be 1. Like that. So that's the midway point right there. Negative 2 over pi plus 1. And then you have to do the same exact thing to get the other 2 points. Now, because we have a lot to do today, can I skip that part? Yes? Okay, so now what we need to do is figure out what's happening between at these points, right? At all 5 of those points. So let me first start off. I know that this one should be here, this one should be here, this one should be here. Why is it that I know those 3 dots look like that? Because it's a sine curve, right? If it were a cosine curve, I couldn't do that. But it's a sine curve, so I know that I have 3 x-intercepts. Now, we need to figure out if this one was above or below, and if this one was above or below. So you would actually have to figure out what that point is. Do you want me to do that, or you're okay? Was this the hardest part right here? Yes. Yep. Now let me show you how you would plug something like this, just to show you how you would plug that into the function. All right, so if I take this, I should get 0 when I plug that in. Now let me just verify. I'm going to go way up here to this. I'm going to just go 4, so I'm plugging in. I'm replacing the x, right, with what? What's that middle point I'm going to use? Negative 2 over pi plus 1. So negative 2 over pi plus 1. And then I still had out here plus 2. Now I'm ignoring the minus 5 right now, right? Ignoring the minus 5. So if I plug this in, let's see what happens. When I distribute this pi through, what happens? The pi's cancel, so I get what? Negative 2, right? Then I distribute through here, and I get what? Plus pi. And then this 2 is still sitting here, isn't it? That pi did not distribute through to the 2. Are y'all with me or not? Yes? These 2's cancel, and I'm left with what? Basically sine of pi. And what's sine of pi? So you go to your unit circle, you think about where pi is, right? Pi is 180 degrees. Sine of 180 degrees is 0. So that should be 4 times 0, so that's 0, right? The whole thing gets zeroed out. That make sense? Okay, so again, because of time, you would plug in, I believe, was the first one above? Yes? And then the second one was below. So you know your curve goes like this. And then to finish it off, you would have to what? Move the whole thing down 5 units. So because you know that this is, that's 4 right there, isn't it? You know that when you move that down, it's going to be like right here somewhere. So your final answer should be something like this. You can go off here. It's terrible. Something like that. Is that good enough to answer your question? Yes? Okay. All right. Anyone else need to turn this in? No? Go ahead. All right. Okay, so today we're going to start Chapter 8. And the title of Chapter 8 is analytic geometry. It is the opinion of most of the faculty that teach here that we should have a course just on analytic trigonometry. That if you're going to take Calculus 1, you should take like a college algebra class that does a lot of algebra, like hardcore algebra, and then you should take an analytic geometry course before you get to pre-cal. Before you get to Cal 1. Unfortunately, the state thinks that pre-cal is enough, and so it's just one chapter in our textbook. But there's a lot of information here, and what we're going to do is hit the high points of it. All right, we're not going to get as deep into it as I wish we could. We just don't have time. So the first section, 8.1, has to do with the inverse sine, cosine, and tangent functions. Would someone mind shutting that door, please? Thank you. All right, so I'm going to introduce this by reminding you not only what a function is, but what an inverse function is, and what the relationship of the functions are visually and algebraically. Because if you understand that basic concept, it's a little easier to swallow the pill that I'm going to be giving you this morning about sine and cosine tangent inverses. So I'm going to say here, recall. This will be my first note. Recall the idea of a function. When you have a function, you basically had an input and you had an output, right? We've seen this many times now, right? The input, you send something through this function, which we call f. It comes out the other side as something else, usually something else, right? And then the question becomes, is it possible to come up with a different function that would send that back to where it came from? So can you come up with something that would take you back? Question, you know? So I'm going to put dots here to represent, these are like numbers, right? You plug a number into a function, it spits out a new number. Is there a function that you can take that answer and send it back to where it came from, right? If you can figure out a function that takes it back to where it came from, then that function is called the inverse, all right? So, and we labeled it with f with a little -1 up top. Y'all remember seeing that notation? That's the inverse function. So let's start with a very simple example and see that we run into problems pretty quickly when our functions have a certain characteristic to them. So here's an example. Here's f of x equals x squared. All right, so I plug something into that, it spits something out, right? I plug in, let's say I'll make a t-table over here. I plug in some x's, here's my x squared, what comes out. So if I plug in 0 into this function, what does it spit out? 0. If I plug in 1, it spits out 1. If I plug in 2, it spits out 4. If I plug in 3, it spits out 9, right? Can I plug negative numbers in here? Can you square a negative number? Sure. If I plug in -1, -1 squared gives me +1, right? -2 squared gives me +4. -3 squared gives me +9. Agreed? And if we look at the graph of this, x squared, hopefully we're all familiar with the idea of this being a parabola, right? So it opens like this, goes up, goes like this. Is this all okay? We comfortable with this? Okay, how is it when someone gives you a graph like this, how can you quickly check to see if it's a function? What do you use? You remember? Vertical line test? Do y'all remember that thing, vertical line test? So what we did is we looked and we said, hey, I'm drawing vertical lines. Do I ever hit the graph more than one time? No, right? I don't. I draw vertical lines. Every single line that I draw hits it no more than one time. So that's what you do to check that this is a function. So indeed, f of x equals x squared is a function. The question is does it have an inverse? So we plug things into x squared, it spits things out. Can you come up with a function that would send it back to where it came from? What do you think? Can you, if I gave you, instead of saying I plug in 0, it spits out 0, I plug in 1, it spits out 1, what if I do it the other way around? I need a function when I plug in 0, I get 0. When I plug in 1, I get 1. When I plug in 4, I get 2. When I plug in 9, I get 3. What do you think? What would undo the squaring? The square root, wouldn't it? Do you all agree? Like the square root of 0 is 0. The square root of 1 is 1. The square root of 4 is 2. The square root of 9 is 3. So it appears that that would work, correct? Yes? So let me put this down over here on the side and put a question mark. Is the inverse function the square root of x? I mean, it appears that it's going to work. But do you see where we're going to run into a problem? Yeah, like if I said plug in 9 into this, what are you going to spit out as an answer? Right? If when I say plug in 9 right here, what are you going to spit out? 3, right? But wait a minute. Over here, 9 came out twice, didn't it? Going this direction from left to right. So if I just give you 9, how are you going to know if it came from the 3 or the negative 3? How are you going to be able to determine that? You can't, right? There's no way, unless I told you it came from 3, now send it back, you would know to send it back to 3. Or I said it came from negative 3, now send it back, and now you know it came from negative 3. But if I just tell you, hey, something got squared and it's 9, tell me where it came from, you have a 50-50 chance of getting it. Does that make sense? So what was the test that we ran in college algebra, the quick test when we looked at a graph, to see if a function had an inverse? Not to see if it was a function, but to see if it had an inverse. Do y'all remember? Not the vertical line test. Horizontal line test, do y'all remember that? Ever hearing that? What you did was, instead of drawing vertical lines, you draw horizontal lines. And if you draw horizontal lines, I mean, right there, I already broke the rule. If I draw a horizontal line, how many times did I hit it? Twice. That means this function does not have an inverse. Because, again, if I go up here and said that that was 9 units high, those 2 points lie on that parabola, right? The one over here came from where? And the one over here came from where? So this one came from, that value of 9 came from what x value? 3. And the other side, this 9 came from what? Negative 3. So do you see that anytime you have a graph, if you draw a horizontal line and hit it more than once, you have multiple places that value came from. So you don't know where to send it back. Does that make sense or not? It's critical for today that you understand that geometrically. So is there a way around this? I mean, can I fix it? And the answer is yes. So I'm going to just finish this off, and we're going to start this example over. I'm going to show you how we're going to fix it. So I'm putting here no. Okay, does not work. Okay, that is not enough for me to just say the inverse function is square root of x. So let me do something else on the next example to show you how I'm going to fix it. Okay, so now take the same example. I'm going to define a function, f of x equals x squared. So I haven't done anything different, have I? Okay, here's the difference. I'm going to put here with x greater than or equal to 0. What I'm doing here is I'm saying, here's a function, but you're only allowed to plug in values that are bigger than or equal to 0. You are not allowed to plug in those negatives anymore, all right? And by doing it this way, when I graph it, instead of getting the entire parabola, I'm only going to get what? We'll get that point, right? 0, 0. I will get this still, because I said you could plug in 0 here, couldn't I? Didn't I? By saying x could be greater than or equal to 0. So I can plug in 0. I can plug in 1. I can plug in 2. I can plug in 3. So I'm going to get the right side of this parabola. And that is it. On a t-table, if I drew a t-table, I wouldn't have those negative values in there, right? Only the positives. Now, when you look at that, is that a function? Does it pass the vertical line test? Yes. Okay. It passes the vertical. Does it have an inverse? Well, does it pass the horizontal? Yes? Everywhere I draw a vertical line, I hit it no more than one time. Everywhere I draw a horizontal line, I hit it no more than one time, right? Because I've cut that left side off. Now, you may be saying you're cheating or something, but I'm not. What I'm doing is what's called a domain restriction. I'm restricting the domain of the function so that the inverse does exist. Now, I cut the left side of this graph off, didn't I? Could I have instead cut the right side off and draw the left side? Yes, and you would still have a function and it would have an inverse. So why did I choose to do the right side? Well, because that's what I chose, right? But I could have done it the other way. So the inverse of this function is exactly what you thought it would be. It's the square root of x. But again, we have to maintain that restriction that we're only looking at positive x's. Now, we kind of know that already because of this. Does this make sense? Okay, now let's talk about what today is about and what Chapter 8, Section 1 is about. It's about finding the inverses of sine, cosine, and tangent. So let's start with sine. Inverse sine. What I'll do is I'll start with the graph of sine. And hopefully we're not going to get too detailed here. We know sine, the sine curve goes in each direction forever, right? The normal y equals sine x. Amplitude of this is 1. What's the period of this sine curve? 2 pi. So we know all these little details of where things happen, right? We know that halfway over here on this period is pi. We know that this right here is pi over 2. We know this is 3 pi over 2. And we could actually go the other way, right, and start labeling things over here. I'm going to label a couple of them just because they're going to become important. This is negative pi over 2 here. This is negative pi. That should be enough. We all good with this? Okay. Is the sine curve a function? Does it pass the vertical line test? Yes. I draw vertical lines. Doesn't matter where I draw them. I'm going to hit it no more than one time. Okay. Does the sine function have an inverse? You're going to run into a major problem, aren't you? I mean, if I draw this one right here, how many times do I hit the sine curve? Infinitely many, right? That line goes in both directions forever, and so does the sine curve. So I'm going to, everywhere I have these little humps right here, there's more over here, there's another one over there, there's another one here, there's another one there, right? There's infinitely many places that intersect that sine curve. So there's no way at all that I'll ever be able to define an inverse function if I don't restrict the domain. Agreed? I have to be able to cut this thing off somewhere so that I only get one answer when I try and go backwards. So I need to see somewhere in here that I can cut the domain off, still, this is important, still get the full range of sine. So I still need to, wherever I cut it, I need to include all the way from -1 all the way to 1. I need all of it there. But I want to make sure that when I cut it and I draw horizontal lines, I don't hit more than one time. So tell me, can I do this? Can I cut it? No. Let me get that horizontal line out of here. How about if I cut it right there and just look right in here? Is that a function between there and there? Is it a function in there? Yes. Does it pass the horizontal line test? No. So that won't work, right? Also, am I getting the entire range of sine? Am I getting the whole thing there? No? So that's not going to work. So how about I cut it? Let me see. Could I go cut it right there and maybe right here like that and look inside here? Is that a function right in there? Does it have an inverse in there? Yes? Do you get the whole range of sine, all the way from +1 to -1, all of that? Yes? That would work. I agree, that would work. Okay? But that's not the way we do it. All right? We have to agree, because you could do that, or how about this? How about if I cut it here and use that piece? Would that work? It's a function, right? Has an inverse. It includes the entire range of sine. So that one would work just as well as the other one would work. In fact, there's infinitely many places I could cut it to make this work. So we, as math people and people who are going to use this stuff, right, had to agree upon where we would cut it. And we say we all are going to cut it there. Whenever we talk about the inverse of sine, we're all cutting it in the same place, that there's no confusion. And the place that we chose to cut it is right here. We cut it off at -π/2 and π/2. So what we'll do is we will come over here to our sine curve, and we will put a restriction on the x. The x that we have here, what you plug in, must be between -π/2 and π/2. Has to be always the case if you want to talk about its inverse. Now, the inverse trig function is just going to send back, right, to send everything back to where it came from. So the way we write the inverse is like this. Sine with the little -1, like that. That's the inverse function. Now, let's be kind of careful here. When I plug values between -π/2 and π/2, when I plug values like this into this function, it spits things out, right? In fact, if I plug in -π/2, I'm going to be down here, it'll spit out -1. And as I move across, the sine curve is going to get, their negative values, they get smaller and smaller until they get to 0. And then as I go to the right more, now we're positive values, they're getting bigger, and the maximum they get is what? 1, right? So I know that what comes out of sine, right, what comes out, the range, is between -1 and 1. Yes? So when I talk about its inverse, can I plug 2 into this? Well, if I plug in 2, I'm saying, go back, where did 2 come from? Well, does 2 come out of sine? Look at this right here. Is it possible to get up here to 2? No. The only things that could possibly come out of this curve are between -1 and 1. So when we talk about its inverse, the inverse of the sine, we have to restrict its domain to what's possible as far as what comes out of sine. So how should I restrict this? Between where and where? -1 and 1. This is a vital point. What I'll do is below this, I think I'll put a little t-table so you can really kind of see what's happening here. If we have x here and we have sine x here, I could plug in like 0, -π/4, -π/2, π/4, π/2. I'll give you a minute to catch up to me here. Okay, so what we're doing is I'm looking at a few values, not all the values, but I'm looking at a few values between my domain restriction, right? So my domain restriction was -π/2 to π/2. I decide to pick π/2, -π/2, -π/4, 0, π/4, and π/2. I'm just going to plug those in. Let's see what comes out, right? So -π/2 on our unit circle, -π/2 is straight down, right? What's sine is the y-coordinate. What's the y-coordinate when you're straight down in the unit circle? -1, right? How about -π/4? So we go and we rotate by, -π/4 is this way. What's the y-coordinate when you're at negative pi over 4? Negative root 2 over 2. What's the y-coordinate when you're at 0? So now don't rotate, right? Just stay there. What's your y-coordinate? 0. How about at pi over 4? What's sine of pi over 4? So rotate up. Root 2 over 2. And then last one, pi over 2, sine of pi over 2 would be 1. So again, what I'm trying to get you to see is what this restriction here means. When we say negative pi over 2 to pi over 2, we're saying the left side here, the only things you can plug into the sign, right? The only things you can plug into the sign have to be between here and here. But when you try and go backwards, right, you're going to go from the right side back to the left side through the inverse function. These are the only things that you can plug in. And I hope that it's obvious that you could never, what, plug 2 in to the inverse sign? Because 2 doesn't come from anywhere. Now, could you plug in 0.7 into the inverse? Yes. Now, we can't tell you exactly where it comes from right now, but I can tell you that 0.7 is between negative 1 and 1, so it's got to come from somewhere, right? That makes sense? Okay. All right, so these are our restrictions, and let's just play with this a little bit and see if we can kind of get our heads around what's going on. So I'm going to give you a couple examples. 8.1.3 examples. Find the exact value Okay, the first example, A. What is the inverse sine of 1? All right, so first of all, I'm dealing with the inverse sign here, right? The inverse sign. And on the side here, I'm just going to remind us, when we deal with the inverse sign of x, the x has to be between negative 1 and 1, right? Anytime we deal with the inverse sign. So we go ahead and verify that what's being plugged in is between negative 1 and 1. That is good, right? So what's going in here is good, right? That's okay. And now what you're doing is you're thinking backwards now. You're saying, remember sine gave us the y-coordinate? Yes? Where is my y-coordinate 1? At what angle? So where's the y-coordinate 1? Straight up, right? What's that angle? 90 degrees or pi over 2, right? So your answer here should be pi over 2 in radians, and then, of course, you could say 90 degrees. See, we're thinking backwards. Do you see why it's so important when I was trying to get you to understand the unit circle? Because if you understand the unit circle, you're just trying to pick points off this thing. How about this? Part B. What about arc sine of root 3 over 2? I forgot the inverse sign, sorry. I said inverse sign. We also say arc sine. I'll use that notation here on the next example. So what you're saying to yourself here first is root 3 over 2 inside my domain. Yes? You could verify it on your calculator. Square root of 3 over 2 is in your domain. And now you're saying because it's sine and because it's the inverse, I'm looking backwards. Sine tells me y-coordinate. I want to know when my y-coordinate is root 3 over 2. So where did that happen? Draw a circle over here. It happens, the y-coordinate is, it's up here, right? Yes? But isn't it also over here? So which one is it? Look on your unit circle. On the y-coordinates on both of those, they are the same, aren't they? So which one is it? Both? It can only be one. Remember, this is where we run into the problem of, you can only go back to one of them. What was our restriction? What was our restriction up here back with our angle? Our angle must be between negative pi over 2 and pi over 2, right? We had to cut that sine function off. We could only look at it here in order to talk about its inverse. So when I come back over here and I'm saying, wait a minute, hold on, it's one of these two, I need to remember that I have to cut the entire second and third quadrants off my picture. Why? Because when you restrict between pi over 2, that's straight up, and negative pi over 2, which is straight down, you're only allowed to swing in these two quadrants. Do y'all see that? And that forces you to be that answer. Yes? Okay. So your answer should be pi over 3. So just keep in mind, because these are the little tricky things that get you on the test. If you have an inverse trig function, your domain has to be restricted. It's going to have to. You remember how we were getting those general solutions a while back where it was like 2 pi n? Were we using n? 2 pi n or pi over 2 n? Do you remember that? It's been too long. All right, there's no general solutions here. It's one answer and one answer only. Okay, how about this one? Yes. That's it. You'll always be in those two quadrants. That's it for inverse sine. You just cut the left side of that circle off. Okay, how about this one? I'm going to use a different notation. Arc sine negative 1/2. Now, what I'm trying to show you here is that there are two standard notations for the inverse sine used in mathematics. The first notation is a sine with the little negative 1 up there, which is pretty similar to what we've seen in the past, right? With inverses, you put the little negative 1 up there. But because of the issue of people using the inverse trig function so much in like technical papers, back when you're trying to write this big paper and typing things up or putting on a word processor, it's easier to write arc sine than it is to do this because superscripting is harder than just writing, typing ARC. You know what I'm saying? So this is just a convention that we use that's a little bit nicer, makes things flow easier when you're trying to type something out. So arc sine and sine inverse, same exact thing. So you're saying, okay, is this between negative 1 and 1? Is negative 1/2 between negative 1 and 1? Yes. So you're good to go on that. Now, because it's arc sine, you're looking at the y coordinate. You're going off your unit circle. Where's your y coordinate? Negative 1/2. Negative, what is it? I heard it was correct. Okay. Yes and no. You said 11 pi over 6? Is that correct? 11 pi over 6, you're looking right there, aren't you? Now, I agree that if you go all the way around and come through here, then you are at 11 pi over 6. But you're not allowed to go through the second and third quadrant. The most you can do is just go backwards. So what would also get you to 11 pi over 6, but just going backwards a little bit? What is it? How much is that rotation backwards? 30 degrees, right? 30 degrees backwards, that's negative 30 degrees, or negative pi over 6. You see the difference? Okay. I'm glad you said that. See, if you would have said 11 pi over 6, then if you go back to our restriction on sine, 11 pi over 6 is not in here. So it'd be like, I'm asking you, I'm saying cut your sine curve so that we can talk about an inverse. I want to know when it was negative 1/2, which would have been down here somewhere. And then your answer would have been 11 pi over 6, which would have been over here, which is not in our restriction. Does that make sense? Okay. Last one. And then we'll start talking about the inverse cosine. What about arc sine of negative 5/4? What do you think? It's not between -1 and 1. What's not between -1 and 1? -5/4. -5/4 is like -1.25, isn't it? This is -1.25. Remember, for the arc sine, we have to be between -1 and 1. This is outside of that. The sine function will never take that value on, which means that your answer is basically that this is undefined. Undefined. All right, we all clear on this? All right, so let's move to our next note. I asked you to find the exact values. I want you to notice that on every one of these answers that we've had here, except the undefined, these are nice values, right? These are things that we're familiar with on our unit circle: pi/2, pi/3, -pi/6. If you were to look at those as decimals, though, they would be messy, wouldn't they? Like pi/2 would be like 3.1415 divided by 2. It's some weird decimal. So this exact answer is preferred when we can get it. But it relies on these being nice points that were on our unit circle, right? So what happens when I put something in here that is between -1 and 1, but is not on your unit circle, right? We know it comes from somewhere, but where does it come from? This is where your calculator comes into play. So everyone break out your calculators. I hope you're bringing them every day now. Find values. So notice I put find the values, but I didn't say find the exact values. And that's because we won't be able to. So let's try, what is arc sine of -3/4? Arc sine of -3/4. So you would say to yourself first, is -3/4 between -1 and 1? Yes or no? Yes? Okay, so that is a good value to plug into an inverse sine function. I'm going to my sine is the y coordinate, so I'm going to my circle. I'm looking for a y coordinate of -3/4. So I know it's down, but I don't know that angle. It's not on my unit circle, right? Yes? So we have a function on our calculator. It's usually the button that has sine on it. It's right above it. It's like you have to hit shift first or second first. Go ahead and try and plug in, if you don't like this number, try and plug in -0.75 into your calculator for that inverse sine, and then tell me what you get. Okay, hold on. Let me grab my negative what? 48.1? 0.5. So you're getting -48.5. Well, that's what we're going to talk about. Anyone got something different? -0.84. Anyone get anything different than that? No? Anybody having trouble getting this on their calculator? Now's the time. Okay, so one of these answers is in degrees and one of them is in radians, and that depended on what mode you were in when you did it. You were in degree mode, I'm guessing? You don't know? Okay. You were in radian. Okay, so we will have to check. I'll show you where to tell. Does everyone know how to switch from degree to radian on their calculators? If you don't, please get with me, because you do not want to take a test and be in the wrong unit and then get everything off, all right? So if you're in degree mode, then you would have to make sure you put a little degree symbol above this answer, -48.5 degrees. If you're in radian mode, you do not have to put anything. You just put -0.84. And it's understood that it's radians. We clear? Is this answer, Negative 48.5. Is it within our restriction? Remember we said our angle had to be between negative pi over 2 and pi over 2? Negative 48 degrees is within negative pi over 2, so that's okay. How about this one? How can you tell there? Well, it's negative pi over 2 and pi over 2. I'm going to put pi over 2 in my calculator. Pi over 2 is 1.57. So you need your answer to be between negative 1.57 and positive 1.57 if you're in radian mode, which that works. The book, I think in the homework assignment, when you get to this part, is giving the answer in the back of the book all in radians. So it's not going to give you the degree answer, just FYI. Okay, let's try on our calculator real quick. What's arc sine of 0.5? Now 0.5 is a half, isn't it? So I want to know where the y coordinate is a half, so I actually know that that's at pi over 6, right? Isn't that what this really means? Pi over 6? But what does your calculator tell you in radian mode? 0.52, what? 36? Okay. Now, just real quick, on your calculator, find your pi key, do pi divided by 6. You should get the same answer, right? I'm just showing you the difference. If I said on a test, find the value, this would be correct. If I said find the exact value, this would be incorrect. Because the exact value is pi over 6. This is the approximate value, because you round it at some point. You with me? Okay. And now you can do this for anything, really. I mean, you can go back and you can recover the angle through the inverse as long as what's in here is between negative 1 and 1. You want another one, or are we good? Oh, try arc sine of 2. See what your calculator says. Arc sine 2. Error. Error domain. So it knows that you can't do that. All right? Yeah, you would say undefined. Yeah, don't put error on your, like on a test, don't put error. You need to know that that's undefined. Yeah, undefined. All right, so 8.1.5. Properties of inverse functions. So here's one of the big results, all right, is that, remember, if I go back to the problem we had when we were squaring something, like x squared, and then we did square root and sent it back, right, in the very beginning? All right, that's basically saying that if I take something, send it through a function, and then send it through its inverse, it goes back to where it came from. So if I start out with 2, I square it, I get 4, I take square root, it goes back to 2, right? So going through both the function and its inverse leaves it unchanged. Or if I start with x, I square it and then square root, it comes back as x. And that's what this property is going to tell us. It's saying that if you take the inverse of the actual sign of something, so if you are an x value, right, the x first gets plugged into the sign, right? Gets plugged in there. After it comes out, it goes through the inverse. So it should come out completely unchanged, and it should come out to be just x. Do you all agree with that? Yes? All right. But we had some restrictions. But negative pi over 2 must be less than or equal to x, must be less than or equal to pi over 2. I'm going to draw a little line here connecting, which means that this property works, okay? If you take sine inverse of sine of x, these two will kill each other off. But you better give me an answer that's between negative pi over 2 and pi over 2, because if you don't, then that means you were not allowed to use the inverse sign. Because the inverse sign says, hey, I've got to have some restriction in there. Y'all okay with that? All right. The next part says that if we take sine of the inverse of x, it again comes out unchanged, but this time the x has to be between negative 1 and positive 1. So this is just two different ways of doing it. You send the x through a function, then through its inverse, it comes out unchanged. Or if you send the function through the inverse first, then the function, then it should come out unchanged. Doesn't matter which order you do it. Is that okay with you? Y'all see the idea here? So let's see how we can put this property into play here. 816. What if we have, for example, a sine inverse of sine of pi over 8? Well, you know what? Let's make it a little easier. Pi over 6, just to start off. What should the answer be? Should be pi over 6, shouldn't it? Now, the only thing that you need to make sure of is that that pi over 6 in here was within that restriction. Is pi over 6 between negative pi over 2 and pi over 2? Yes? So this should just be pi over 6. There's no work to be done. I'm going to say since pi over 6 is between negative pi over 2 and pi over 2. Compare that to this. What do you think most people say this is? 5 pi over 3. And that would be incorrect. Why? Because if you're saying it's 5 pi over 3, 5 pi over 3 is bigger than pi over 2, isn't it? So you can't possibly get 5 pi over 3 to come out of this. So the way we have to do this is we have to do it a little bit more mechanical. Go back to the beginning of when we were learning about the unit circle. This meant sine of an angle meant you look at the y-coordinate, right? So where's 5 pi over 3? Where is it? What is sine 5 pi over 3? What angle is 5 pi over 3? What quadrant am I in? Fourth quadrant? Fourth quadrant? So this right here, where is it? Down here like this. Is it that one right there? That angle there? Okay. I'm supposed to be between negative pi over 2 and pi over 2. Can you make that an angle between negative pi over 2 and pi over 2? Instead of coming all the way around, can you have gotten there by just going backwards? Yes? And what would be that backwards rotation? By how much? So negative 60 degrees or negative pi over 3. Do y'all see that? But I'm going to do this slightly different, okay? Just look at this real quick. What is this? What is sine of 5 pi over 3? What is it? Okay, so that's sine inverse of negative root 3 over 2. Do y'all agree with that? Without having to worry too much about what's that backwards angle. Just if I say sine of 5 pi over 3, that means you go to 5 pi over 3, you find me the y coordinate, don't you? It was negative root 3 over 2. Now, forget everything else. Tell me what this is. Now, that's what we just did in the previous example, isn't it? Now I'm asking myself, where is the y coordinate negative root 3 over 2, but I have to be between negative pi over 2 and pi over 2. And you said that that was what angle? Negative 60. So negative pi over 3. We're going to do another one of these just to make sure you're following this. The moral of the story is this. If the angle you're trying to plug in here is between negative pi over 2 and pi over 2, then your answer is just that angle. But if the angle you're trying to plug in here is outside of that, you actually have to work it through a little bit. Okay, let's do this one. See, how about sine inverse of sine of seven pi over 6. What does that equal to? So we do a quick check. 7 pi over 6. Is that inside the interval negative pi over 2 to pi over 2? No. So that means we're going to have to just grind this one out. Forget the sine inverse for now. What is sine of 7 pi over 6? So you go to 7 pi over 6 on your unit circle, right? You find the y coordinate. What's the y coordinate there? Negative 1/2. I'm out of room. Do we agree with that? The inside here is negative 1/2. And now what we do is we forget this for a second. Just forget that even happening, and just start this like it's its own brand new problem. When I'm saying sine inverse of negative 1/2, I'm going to my unit circle. Right? I'm cutting the left side of the circle off. Why? Because I'm talking about arc sine, right? I have to cut the left side off. And I'm asking myself, because it's sine, where's the y coordinate negative 1/2? And that happens right there. And that angle is negative pi over 6. So your answer here would be what? Negative pi over 6. Do you see how this can be a little tricky if your angle's outside of negative pi over 2 and pi over 2? Questions, comments, concerns, gripes? We're good? Okay, let's move on to the inverse cosine. This will go a little quicker because now we've kind of developed the idea. What am I at here? 817. The inverse cosine. So we take a look at our cosine curve. Sorry, that's one of the worst pictures I've ever drawn in my life. That's what cosine looks like. It has a period of 2 pi. The difference is that it starts out at 1, right? And then it comes down, then back up, and then stops at 1 again. Definitely is a function, passes the vertical line test, fails the horizontal line test miserably, right? Again, I need to cut it somewhere. I can cut it all these different places to make it work. We all had to agree on one place. The place that we decided to cut it, that we all agreed on, was between here and here, looking in that region and cutting all this crap off. So what is my restriction on the cosine? 0 to pi. On sine, it was negative pi over 2 to pi over 2, right? So it's a different restriction for cosine than it is for sine. You have to remember that. It would be nice if they were the same, but they can't be the same, can they? What if I had tried to cut it the same way I cut cosine, between negative pi over 2 and pi over 2? Would that have worked? No, I just get that top hump there, right? That would fail. So I couldn't do it the same as sine, unfortunately. All right? So I had no choice. So here's what we have for the inverse cosine. We take the cosine, y equals cosine x. We restrict x between 0 and pi, and therefore the inverse cosine will be its inverse function. Now, the restriction on the inverse is the exact same as it is for sine. In other words, the negative 1 to 1 is still going to be the same because cosine is still between negative 1 and 1. It's just the angle that comes out is going to be different. Now, we saw the value of the unit circle earlier. With sine, when we were trying to go backwards, we cut off the left side, didn't we? What are we going to cut off when we're trying to go backwards for cosine? If we're between 0 and pi, our angle is between 0 and pi, right? Somewhere in here, right? So we're going to cut off the bottom 2 quadrants. So any answer we get in terms of the angle is going to have to come from one of the first 2 quadrants for our cosine. We good? Okay. So let's see a couple of examples of this one. We'll find some exact values, then we'll use our calculator to get some other ones. Then we'll show the properties again, and then we move on to tangent, arctangent. Is this kind of flowing naturally from sine now? I mean, it's just extending it to a different curve? All right. Find exact values. What is arc cosine of 1? All right, so let's go back, think through this again. If we're dealing with the inverse cosine function, I need to make sure that what's in here is between where and where. That's what will come out. But what's in here has to be between negative 1 and 1, right? Our answer is going to have to be between 0 and pi. So it is between negative 1 and 1. And now we're asking ourselves, where on the unit circle is the, which coordinate this time? Correct. But when we're doing sine, we're looking at the y coordinate. When we're doing cosine, we're looking at the x coordinate. So this is basically saying, at what angle is the x coordinate 1? Where? 0. And if you draw a quick circle here, right there, that point, and that's okay, I've cut the bottom 2 quadrants off. That point does lie between 0 and pi, so our answer would be 0. How about, what's arc cosine of negative root 3 over 2? So is negative root 3 over 2 between negative 1 and 1? Yes? Okay. And so you're looking on your unit circle. Where is your x-coordinate negative root 3 over 2? But you can only be in the first 2 quadrants. So what is that? What angle is it? 5 pi over 6. Here's a circle to go with that answer. Right? Where is the x-coordinate root 3 over 2? It happens right there. We okay with that? Arc cosine of 0. Good. Yes? Anyone else? Got one answer that was correct. This is saying, where is your x-coordinate? 0. Right? Pi over 2. Straight up. I really hope that when we were going over the unit circle, and I was trying to get you to understand the relationship between sine and cosine on the unit circle, that you really got that, because it's obviously going to make this a lot easier if you can see where things are. What would arc cosine of pi be? Ooh, that's tricky. Negative 1? This always gets students. It's like almost a trick question, trying to confuse you. The key to it is to understand we're dealing with the inverse cosine here, right? If I said, what's cosine of pi, you would go to pi, which would be where? Over here. And you would go to the x-coordinate, which would be negative 1. If it was cosine of pi, that's not what we're saying. We're saying, what's the inverse cosine of pi? So now we're saying, where is the x-coordinate, where is it pi? See, the calculator's coming out. What'd you get? Error? Why are you getting an error? That's right. This is not between negative 1 and 1. Pi is 3.14. This is an error. But see, it tricks you, because what happens is in pre-cal students, as soon as they see angles, they're thinking, okay, I'm going to go to the angle, right? But that's not what's happening here. I'm actually trying to plug in a number that's bigger than 1 into an arc cosine. You can't do it. So this is going to be undefined. I'll show you another example of this as we move to the next set of examples. So 8.19. Find the values. So I'm not saying exact values, right? Just find the values. What's arc cosine of 0.23? So is 0.23 between negative 1 and 1? Yes? All right. If it's between negative 1 and 1, plug it into your calculator and tell me what you get. 1.33? Did you change your mode, or are you still in, what is it? It's in radians now? Anyone do it in degrees? 76.7? And then I have to put the degree symbol there. Now I want us to think about this for a second, because this is going to become pretty important later, all right? If we're at 76.7 degrees, 76.7, that's somewhere up there, right? About there? We're definitely not in the bottom two quadrants, which is good because we were talking about the arc cosine. We're saying to ourselves that if you rotate to 76.7 degrees like this, and you look at the x-coordinate should be what? What's the x-coordinate here? 0.23, right? Because we're saying, okay, where on the unit, this means right here, where on the unit circle is the x-coordinate 0.23? So 0.23 up there, somewhere up there, right? That angle turned out to be 76.7. All I'm doing is drawing it to verify that, yes, it does look like my x-coordinate is 0.23 here, right? If we would have come up with an answer and it would have been something like 10 degrees, right? 10 degrees would have been like somewhere in here. Your x-coordinate there is definitely not 0.23, so something's wrong. Do y'all kind of get that? You can kind of reverse it, engineer, and think through it and see where things are. Yes? The y would have to be what you get when you do inverse sine, right? Inverse sine. But you would actually have to take sine of this angle to get the y-coordinate. This inverse cosine only deals with the x-coordinate. That's all it tells you. Okay, how about this? So you might look at this and say, pi over 2. I rotate by pi over 2. Cosine is the x-coordinate. You may be thinking that this is 0. But it is not, because this is the inverse cosine. This is just a number I'm plugging in, right? Pi over 2. Is it between -1 and 1? Pi divided by 2? No, right? So what's this going to be? Undefined. Please make sure you understand the difference between that versus this, right? Difference between these two. This one, you're trying to go backwards to find the angle, right? This one, you plug in the angle, which means you rotate by that much, and you look at the x-coordinate, which is, in this case, 0. So the answer to this would be 0. Do you see the contrast, the difference here? Something you can do to kind of try and remember what's going on here is that if you look at this whole idea of functions, if you do sine x, or you do cosine x, or you do tangent x, those are the only three we're going to do today, those send something from their domain over to something, right? The functions map a number over to a number. The number we plug in general, is an angle, right? An angle is what goes into a trig function. What comes out is a number. Cosine of 0 is 1. Sine of pi over 2 is 1. Sine of pi over 4 is root 2 over 2. So when I plug an angle into a trig function, it spits out a number. When you go backwards with the inverse sine function or inverse cosine function or inverse tangent, which we haven't done, then you're plugging a number in, right? And it's spitting back what? An angle, right? So your answer should be an angle. Now sometimes we know the angle, the exact value of it. Sometimes we don't, and we have to use our calculator. Another way of representing what I just said, we do sine inverse of an angle, and it gives us a number. If we take sine of, I'm sorry, didn't I just get that backwards? Yes, I did. Sine inverse of a number gives us an angle. Sine of an angle gives us a number. You could do that for cosine and tangent also. It doesn't matter. The book is sticking to radians, so I would, if you're checking your answer in the back, you should be able to get the radian. But please understand that I think degrees are going to be helpful a little bit later. So be prepared to switch your calculator from radian mode to degree mode, and that way you have the degree answer. See, because if I say right now, where's 32 degrees? Is everyone comfortable with what 32 degrees is about? Somewhere like, somewhere about there. But if I say like 0.5 radians, where's that? It's harder to determine, right? Where's 3.14 radians? 3.14 radians. Well, what's pi radians? Pi is 180, right? And pi is 3.14 about? So when I say 3.14 radians, you have to understand that that's about 180 degrees. It's not as like off the top as degrees are for us. 30 degrees, right? 90 degrees, 125. You have idea of where that is. So that's why I think it's important to be able to go back and forth between the two. Hope that makes sense. All right. The last one, arctangent. .10. The inverse tangent. Now, when I look at the tangent function, it has some interesting stuff happening at pi over 2 and negative pi over 2. The tangent function had those asymptotes, right? And then when you draw it, it looks like it goes down on the left, it goes up on the right like that, right? And then didn't it repeat itself? Like it did the same thing over here, same thing over here, and it just kept on having those asymptotes. And you could just keep drawing these to the left and right forever, couldn't you? So let's just focus our attention on this one in the middle. Doesn't it seem like we have a pretty natural place to cut this thing already? I mean, look at this. These asymptotes almost cut it for us. If we look between here and here, it passes the vertical line test, right? And the horizontal line test if we just focus in here. What's the main difference, though? Look at your range. Bless you. Bless you. Your range, not your domain. The domain looks like between what? Negative pi over 2 and pi over 2, right? But can we actually plug in negative pi over 2? No, because there's an asymptote. Can we plug in pi over 2? No, so our domain is going to be everything between that, and we have a way of writing that. That's fine. But remember, the sine and cosine were bounded between negative 1 and 1. Is this trig function, is this tangent function bounded? No, it goes up to the right forever, and it goes down to the left forever. So it actually takes on every value between negative infinity and infinity. So we have to keep that in mind now when we plug things in here and try and write things out. So we know we're going to cut this thing appropriately. We're going to take our tangent curve. We're going to restrict our x between negative pi over 2 and pi over 2. What's the difference between the way I wrote that and the way I did it earlier? It's not including no equals, right? What other trig function do we restrict between negative pi over 2 and pi over 2? Which one was it that we did? Sine or the cosine? It was the sine one, right? Except for the sine, we could include them. But you just might want to remember that sine and cosine, they do have kind of matching domains. Cosine is the one that has the 0 to pi. It's different. Okay, so that's my restriction. I'm going to define the inverse tangent, arctan. And the restriction here is not between -1 and 1. I can plug in any value, -infinity, all the way to +infinity, anything in there. We never put equals on infinity, because infinity is an idea, it's not a number. So that's our restriction for the inverse tangent. So if you go to your calculator, we'll do it in a second, and you try and take like inverse tangent of 32,492, it's going to give you an answer. You're not going to get an error domain, because it can handle, the inverse tangent can handle any number you give it. It'll spit back an angle. And that angle it spits back will be between where? -pi/2 and pi/2. Okay, so let's try a couple of evaluations here. Find exact value. These will be a little harder. I'll start with arctangent of 0. I'm going to remind you here on the right side that we are cutting off the left 2, aren't we? Because we are still stuck between -pi/2 and pi/2. So our answer's got to come back somewhere in the first or the fourth quadrant. Arctangent of 0. Now, why is arctangent going to be more difficult than sine and cosine tangent, or inverse sine and cosine? Yeah, with the unit circle with sine and cosine, we just looked at the y-coordinate for sine. We looked at the x-coordinate for cosine, right? For tangent, tangent isn't the x or the y. It's the what? It's the y divided by the x, isn't it? It's the y divided by the x. So where is your y-coordinate divided by your x-coordinate equal to 0? At the origin. Yes? What do you mean by origin? Well, we have to be on the unit circle. Right? We have to be somewhere over here. Wherever the y is 0, right? If this top was 0, the x wouldn't matter, would it? So where is your y 0 on this unit circle? You have to live on the edge of it. Isn't that here? Yes? That's the point 1, 0. If I take the y-coordinate and divide it by the x-coordinate, that's the definition of tangent. Y divided by x would be 0. So I am actually getting 0 to come out at this point. What's the angle here? 0. So the answer here is 0. Remember, this is an angle. This is a number. I wanted to know at what angle do I get 0 to come out of the tangent. See how that's trickier than sine and cosine? How about inverse tangent of √3? I want the exact value. You cannot go to your calculator here. So again, you want to know when your y-coordinate divided by your x-coordinate will be equal to the square root of 3. So what does your instinct tell you here? What angle do you think we're talking about here? Like angles that involve what? Your x and y coordinate have to divide through, and you have to have a √3 in there, don't you? Didn't we have some common angles there that had √3 in them? Which ones do you have in these two quadrants? Which angles involve the √3? 30 degrees, 60 degrees, -30, -60, right? But it's turning out to be a positive number, right? Which means that these either both have to be negative or they both have to be positive. Can they both be negative? Why not? Because that would mean you're in the third quadrant. Good. So you know that because these cannot both be negative, you must be in the first quadrant. So you really have like two choices here, 30 degrees or 60 degrees. So let's take a stab at it. If we went to the 30 degrees right here, and we have what? Root 3 over 2, 1/2? Isn't that what we have there? What would y over x there be? If we take the y coordinate and divide it by the x coordinate, you would get, flip that fraction, you would get, are y'all following what I did there? Taking the y coordinate, dividing by the x coordinate, flip it, 2's cancel, get 1 over root 3. Is that the same as root 3? No. So I bet you it's the other way around, isn't it? I bet you it's instead of 1/2 divided by root 3 over 2, it's probably the root 3 over 2 divided by the 1/2, which would be at which angle? At 60 degrees. So if I go up to 60 degrees, this is 1/2 root 3 over 2. And figure out what that ratio is. Root 3 over 2, 1/2. Flipping that, I should get root 3. I won't go through the work. Do y'all see how this is requiring a little bit more thought? So what angle did this happen at? 60 degrees. So in radians, my answer would be pi over 3. Excellent. Getting low on time here. How about this one? Arctangent -1. Sure? Careful. Is it possible to get a negative number in the arctangent here? Yes. Okay. It's the y divided by the x. So can you be in the first quadrant? No. Can you be in the fourth? You have to be in the fourth, right? Because in the fourth quadrant, your x is positive, your y is negative. So the ratio should be negative. Now, what's going to give you -1? Is if the y and x coordinates are exactly the same, right? Just off by a sign? -45 degrees. Negative pi over 4. Do y'all see that? If we go down here to this angle, this is root 2 over 2, negative root 2 over 2. And so that angle there is negative pi over 4. Questions? Just be ready with arctangents to see like the root 3 pop up sometimes, and then this 1 over root 3 will pop up, and just because that's the only thing that's really possible, you know, with these common angles. You can get 0, you can get 1, -1, root 3, 1 over root 3. There's really not a whole lot of other things that can happen. Now, if you don't restrict yourself to an exact value and you have to break your calculator out, well, then things become a little different. If you have something like find the value what's arctangent of 473.4? So again, you're never going to have undefined for arctangent as long as you're plugging in a real number. So you're going to have to go to your calculator to figure that out. And give me a radian, and then someone give me a degree. 1.57 for radian. and something really close to 90. What? 89.8. So that's just using your calculator to figure that out. We okay? Now I have one more note for you, and then I think I'm going to cut you loose. More of the properties cosine inverse of cosine x should be x. As long as the x is between 0 and pi. Go back and look at the one that I did for sine. We said if you put the sine inverse with the sine, we get an answer, but that answer had to be between negative pi over 2 and pi over 2. Same thing, but now with cosine. And it goes the other way around. If you do cosine of cosine inverse, this should be right as long as the x was between negative 1 and 1. And then what do you think? You think we have properties like this for tangent? Yeah, and its inverse? How about tangent inverse of tangent x will equal x as long as the x is what? Between negative pi over 2 and pi over 2. And then tangent of arctangent of x will be equal to x. What do you think for that one? For any value of x, right? Between negative infinity and infinity. Okay, we have 4 minutes. I think that's good for now. I don't think we can get into the rest of this. This will be a good place to pick up the next section. We're not supposed to, well, my schedule says we're not supposed to do 7-2 or 8-2. So I don't think we're going to do 8-2. So on your test, we're supposed to, it says the test will be up through 8-3. It'll be not including 8-2. So let's see how far next class we get into 8-3. I think we'll spend the first maybe hour, 45 minutes doing 8-3, and then we'll spend the rest of the time talking about the exam. All right, let me give you your homework for tonight. This is all out of 8-1. This is going to be page 614. 1 through 51, odd. That's a lot of work, but a lot of it is calculator, and then other parts are just picking the values off the circle, going in just like we did in class. So they should go pretty quick. There's not a whole lot of work that goes into these, so don't be intimidated by how many there are to do there. All right, but please get those done by next class so you don't pile a bunch of stuff up for yourself to have to worry about when you're trying to study. Who's not here? Gosh, got to figure out a way to do that. Take attendance without having to call attendance. I tell you all about my idea for taking attendance. Like when you register for